All right, thanks for joining me tonight. I'm going to talk about ANF and CPS conversion. So the basic issue is this. If we've got a complex expression like this one here, we've got 4 plus the result of read times 3 plus 4 plus 5. So the issue is we translate constructs like plus and times and other primitive operations down to CPU instructions. The arguments or operands of those instructions have to be atomic. They have to be things that, at least the abstraction, I think this is not really how CPUs work anymore, of course, but the abstraction is you need to be able to finish computing them in some finite amount of time. Something like within a clock cycle, or at least some known amount of clock cycles. So here, for example, I've got add of the immediate value 5 to the register RBX. But I couldn't add, maybe the result of multiplying read by 3 to RBX. That's just not something I can do. So what I'm going to do to help get me there is I'm going to basically stay within this language. I'm not going to translate down to assembly, but to make it simpler, I'm going to do this little conversion into this smaller fragment of code where basically I'm going to take any of the complex sub-expressions and I'm going to introduce these so-called administrative bindings. So here I bound read to x0, and then I take x0 here as the result of read, and I can make this expression atomic by replacing this read with this x0 within this context. See? Because now x0 is in scope by virtue of sitting under that let right there. And I can keep doing the same thing and make it so that everything is atomic, and then I can just return x3. So for my class, I have this R1 language here, which I've kind of recapitulated. And you have to translate it down to this R1 ANF language, where basically the idea is that when you add, when you negate, when you let bind, everything has to be atomic. All right, so the question is, how are we going to start doing that conversion? And we're going to start by discussing this technique called continuation passing style. In continuation passing style, you're going to write your functions so that they take an extra parameter as input. That parameter is going to be something called a continuation. A continuation is this convention that whenever you finish executing, you're going to invoke your result, or you're going to invoke the continuation on your result. I view continuations kind of as a bridge between the sort of C++ style of programming where you have an explicit return, right? And this kind of functional style of programming where whenever you compute a value, whenever you reduce to some actual result, well, implicitly in this expression-oriented style, that is the return value. You don't have to explicitly write return in racket to return the value. It's just whatever things compute to, that's the value. Where in C and C++, you do. There's an explicit notion of returning and control flow. And so I see it as kind of a bridge, but between those two methodologies, but that probably doesn't make a lot of sense until you see an example. And so to discuss some simple examples, why don't we think a little bit about how could we walk over a tree in a tail recursive fashion? It's a little bit of a contrived example, but let me just see. Like, let's say, for example, we had a list. Well, if you have a list, it's easy to walk over a list in a tail recursive manner. So say we want to walk over a list and count every, or add all even elements. Add even tail, and then I'm going to have my list, and I'm going to have an accumulator I'm going to use here. I'm going to match the list. If it's empty, I'm going to return the accumulator. Otherwise, if there's a head and there's a tail, I'm going to call add even tail, and I'm going to say here, if head is even, then the accumulator is going to be head plus the accumulator. Otherwise, it's going to stay the same. It's just going to be the accumulator. And now here, notice that this call to add even tail is in tail position. The return value from add even tail is the return value of add even tail. And we're computing the result of this if before the invocation of this call. That's the way the control flow works, right? Because this is equivalent to saying let this intermediate value be this on this intermediate value. And now I can call add even tail. And let's just see the result. It should be, let's turn off these things. You can see the result. And it should be tail of L. There we go. Or rest of L. And there we go, we get 6. So doing this with lists is not hard. It's not hard to write tail recursive accumulating functions over list. But it's a lot harder if we want to do it to trees. So what's a tree? Let's define tree ha t. And it's either going to be the empty, well, let's say it's either going to be the empty tree or it's going to be a node of some value v. And it's nothing else. And now I want to write a function some even tree. And I'm going to take t here. And the obvious way to do it is like this. It's to say the empty tree is 0. If I've got a node of v, t0, and t1, then it's going to be v plus some even tree of t0, some even tree of t1. And now I should be able to do some even tree node 15, node 5, empty, empty, empty. And I get 20. The issue is neither of these calls is in tail position. Now, it's actually really tough to do this. You know, you can't use the same trick because, well, here, if I went down to t0, how would I remember to come back to t1? So if I knew that I was always going down the t0 side or the t1 side, it would be fine. For example, this function, binary search of t for some value v. Here, I can match t, and I can say if it's empty, then the result is false. Otherwise, it's a node of n t0 or v t0 and t1, and I can have a few conditions. I can say if equal v, let's make this v plus so we don't clobber the name, v plus to v, then this is true. Otherwise, if v plus is less than v, then I want to binary search down t0 for that same v. Else, I'm going to binary search down t1 for v. And if I assume that my nodes are sorted, or if I assume that my trees are sorted, then I think this will work out. Okay, that one works. That one doesn't. Okay. So I think I might have gotten the value wrong. So if I am looking for v, and if it is smaller than the current thing, I think I got these wrong, then I want to binary search down t0, right? Yeah. All right. Oops. Okay. So this function is tail recursive. No issue there. But it's kind of hard to imagine how you would do this kind of sum trick where you walked over the whole tree. Here it's easy because we know based on the current v and v plus, do we look at the current one, do we go left, or do we go right? Once we go left, that's just our result. So this is a tail call, right? No issue there. So what's the trick? So the trick is that we're going to do, so sum tree, or maybe sum even, let's call it tree. We're going to have our tree T here. We're going to have a function here called K. And this function K is a continuation, which we must call with our result. So here's what we're going to do. We're going to match T, and if T is empty, we're going to call K on 0, because that's the deal. K is a function. Once we have our result, we have to call K. No other option. What if we're in a node with some value V, and some subtree T0 and some subtree T1? Well, this is now kind of the trickier case. So here's what we're going to do. We're going to call sum even tree. We're going to call it on T0. And then we're going to pass it a new continuation that we're going to define here, which is going to be lambda of T0's sum. Okay. So once sum even tree finishes summing up T0, it's going to invoke this continuation we're defining right now as our second parameter to sum even tree, and it's going to pass it the result T0's sum. And now what are we going to do with that? Well, I think we're going to call sum even tree T1 on it. And we're going to pass it a second continuation that's going to be T1's sum. And then here's what we're going to do. So maybe I could even say define my contribution, or this node's contribution, will be if even v, then it will be v, otherwise it will be 0. So here, what we want to do is we want to return the addition of T0's sum plus T1's sum plus this node's contribution. But the deal is, well, we're supposed to return that, in this case, to the continuation K, because that's our contract. Because we might be sitting under a continuation for some subtree. We want to respect the fact that we're supposed to call this K with our result. So that's what we're going to do here. And now let's try it. Sum even tree, and then node 20, node 10, empty, empty, node 55, empty, empty. And then our continuation to kick us all off, just like in the case of sort of the default accumulator being 0, here we're going to have sort of a default continuation, and it's just going to be lambda xx. And oops, I needed to quote this. So there we go. We get 30. Okay, so this trick right here, what I just did is I implemented a function, some even tree, which was written using this style, continuation passing style. Continuation passing style is a style. Continuation passing style is a style of programming where I augment every function definition to include a continuation parameter. The requirement of the paradigm, maybe I could call it a calling convention of sorts, is that whenever I get my result, I invoke the continuation on that result. Continuation passing style is actually very similar to sort of callback-oriented programming. If you've ever programmed in maybe a reactive type web framework, where you can be able to, for example, add event listeners to things and say things like, whenever the key is pressed, call this function. That's sort of a related concept to a continuation, right? That's a callback. But you can think of continuations as kind of a generalization of callbacks, right? You are passing a callback for what to do when you finish. And then we have this very powerful technique where we can get this kind of inversion of control by calling the continuations and then building up these continuations as lambdas here. So I think this is a pretty subtle trick where if you haven't seen it before, it kind of bears going over a few times, coding this up for yourself and making sure that you get what's happening here. Especially the real magic is in this ability to create this new continuation that gets passed to this call of some even tree. That lets us say, okay, first go explore T0, and then when you're done, call back our continuation with your result, T0 sum. Then call some even tree on T1, passing it a continuation that says get T1 sum. Now you've got both T0 sum and T1 sum, and you can just return because you've got them both. So that allows us to then make this a very simple function, or a simple expression right here, which we can then invoke the continuation on. Okay, so now we're ready to really describe the general technique of being able to translate these kind of complex expressions like this kind of R1E language, the expression language, or these complex expressions that look like this down into simpler expressions. Now, I'm going to teach a fairly simple conversion, really, that's called, well, it's really a continuation passing style that I'm going to be discussing. I'm not going to be discussing the more general ANF transform that's going to exploit two levels of continuations. Both a semantic continuation and a syntactic continuation are sort of at play. And there's some tricks there to be able to make a more efficient compilation of these things. And so I'm not going to talk about that right now. I think that's a pretty complex algorithm. I'm going to try to keep it simple here and show sort of the main ideas relevant to Project 2 in this class that will get you an answer. So I'm going to call it ANF convert expr, and here's what we're going to do. I'm going to define a helper function, which I'm going to call convert expr, and it's going to take an expression, and it's also going to take a continuation. So CE converts a complex expression E. Whenever it's done, we need to pass its result to K. All right, so let's just start coding it up. By the way, to actually scaffold this out, since this is a helper function, let's write the call right now so that we don't get to the end and then get too confused. We're going to pass it expr, and then our top level continuation is going to be the identity function lambda xx. And then here's what we're going to do. I'm going to say match E, and there's a few cases. So let me get my cases from this definition right here. Now, I'm not going to do all of these because I don't want to give away all of the answer. I think I'm going to do Maybe these, I think, seems appropriate. And then I'm going to try to let you figure out the rest. So here's going to be the idea. When it's an integer, we'll just call the continuation on I, because it's already a simple expression. I is already a simple expression, and I'm supposed to call k with my result, which needs to be something simple, or something in ANF, something in a sort of atomic form, and I is already an atom, so I can do that. No issue there. It's going to be the same thing right here. So here I can call k on x. All right. Now, the interesting case is this one. So let's say I've got plus of E0 and E1. And E0 and E1 are not necessarily in ANF. And by the way, ANF is sort of a normal form. I used to think it was administrative normal form, but I've read some conflicting information on it. So just to be safe, I'll say it's called a normal form. The idea is basically that in ANF, everything is a simple expression in the sense that there are no functions being applied to other complex expressions. So things like plus, we have to have atoms as our arguments. Okay, so what's the basic idea? So the basic idea is going to be something that kind of mirrors our tree walking technique. So notice over here, I basically dug into T0, but then I needed to do the rest of the work for T1, and then also to finish by adding up the result T0 sum, T1 sum, and this node's contribution, and then calling k. I'm going to take a very similar trick over here, except I need to be generating basically a let expression. So I need to emit a let expression which captures the result of converting E0 and creates an administrative binding using let and then what I'm going to do is I'm going to invoke my continuation. So then I've got a variable name for the binding, which I can use to invoke my continuation k. All right, so let's see what that's going to look like. So first, I'm going to define an intermediate variable. So this is going to be the result of E0. So this is going to be E0 result. And I'm going to use GenSim. Now, GenSim will just give me a fresh symbol name. So I can call it, gives me back this thing. If I call it with a symbol like E0, it will prefix the result with this thing. So maybe I could call it like intermediate result, something like that. Now here's what I'm going to do. I'm going to say invoke C of E. Start to do CPS conversion on E0. And whenever you're done, you're going to pass me a piece of syntax representing the result of ANF converting E0. So you're going to pass me syntax representing the result of ANF converting E0. And that's going to be probably something like variable name, right? Probably a variable name. Or maybe it was just an atom, I guess. It could be just an integer as well, right? So you're going to pass me some syntax, and here's what I'm going to do. I'm going to emit let of E0 and, E0 result. I'm going to let E0 result be this big thing. And then now I'm going to call K here on this variable E0 result. Except that's not really what I want, is it? I'm sorry, I made a little mistake there, didn't I? No, I don't have the result of E0. I want to be doing addition here, so I'm sorry, I made a mistake. I'm not done yet. So once I get my ANF converted result for E0, I want to keep going, don't I? In the same way that over here in sum even tree, I then called sum even tree on T1, and then the ultimate result I fixed up here. So I'm not quite done, actually. I made a mistake. So what I'm going to do is I'm going to call CE on E1, and then I'm going to get back, I'm going to get this lambda here. Syntax representing the result of ANF converting E1. And now I'm going to say let E0 res be plus of, now this is obviously too long, super silly, right? Let's just call it A0, and let's call this one A1. And what we're going to do is now we're going to call the continuation K on this new variable E0 result. All right. Okay, so let's run this. Now let's run it on CE, and now let's do plus 1, 2, and then we need to pass lambda XX. And of course, it's ANF convert. CE is the internal helper function, which is not exposed to the top level. Okay, so here we go. Notice that I produced this intermediate value here, where I did int 2333173 be plus A0 A1. Ooh, except I made a mistake, didn't I? These should have been unquoted. Because they're not literally A0 A1. This is wrong. They're these things here. There we go. Let's see if it works for larger expressions. Okay, so here we let bind the result of 3 plus 4. Then we use that to be plus 1 of this intermediate, and we return this result. What about something larger? We still get a long stream of LUTs. Now, that's basically the approach. You know, the idea is you're going to want to generalize this. You're going to want to add in some more, right? So let's think about what would minus E be. Now, you're going to want to do kind of the same trick, right? You're basically going to want to call C of E with E. Now, you're going to get back a lambda, which is going to be some atom here. This is going to be an atom, huh? And you're going to want to define a new variable, some intermediate variable. So let's call it x, and this is going to be gensim int. And you're going to emit here, you want to let bind x to be the result a0. And now you're going to call the continuation k here on a0. And now that should get us minus as well. So now if I do ANF convert of minus plus xy plus 2, 3. Ooh, no, I can't do a minus of this. Let's do plus of these two things. There we go. Now I get x plus y. I get 2 plus 3. I generate those two and build up this intermediate variable for their sum. And then I take the negation of that. Ooh, no, I'm sorry. I messed it up here. Here I was supposed to negate a0 in the same way as I did the plus of a0, a1 right here. So let's try it again. So there we go. I can even pretty print it to make it look nicer. There we go. Now, it's going to turn out that this style, this methodology that I've taught you is kind of the basic thing that you would find in lectures on continuation passing style. There's kind of a subtle difference between ANF conversion, at least the traditional algorithms that are in some of the most kind of famous papers, and CPS conversion, the kind of thing you might learn, the sort of more naive sort of style that I taught here, which is also taught in Andrew Appel's book, Compiling with Continuations, very famous book about designing functional compilers. I recommend you stick with this relatively basic style for a while, even though it emits some suboptimal code. And so we'll talk about a little bit later on. For example, if you notice here, there's no reason I couldn't make this, the whole result just be minus of this intermediate expression. There's no need to bind this administrative expression right here. And so things like that are going to happen with this sort of a conversion. And you will end up omitting a little bit of extra administrative instructions, which could be cleaned up via an optimization pass. But it turns out you can actually do that optimization and inlining on the fly if you learn a slightly more advanced version of this algorithm. So I'll discuss that algorithm later on in the course and maybe link to some of the material in this video as well. But thanks so much for joining me tonight. Hopefully this clarified some points surrounding the project. Just to say a little bit about what more should you do. So I think the remaining cases are read and let. For read, here's kind of the idea, is you want to basically gensim a name. You want to also, in the same way as here, I gensimmed an intermediate variable so I could let bind it. I'm going to gensim an x so that I can apply read to it, and then I'm going to use that name and apply it to the continuation. For let, I'll let you think about it a little bit more as well. Basically, the idea is you want to convert E first, and then you want to convert E, B, the body. So I'll let you think about that one and not give away quite the whole solution, but this is a good part of the way towards building this pass in the compiler. Hopefully this helps. Feel free to write me with any questions. My email address is kkmicins@syr.edu. And otherwise, have a great night, and thanks so much.